Hello, good evening, guys. This is your mentor Tom Tulofai speaking. Last week we finished the project that had to do with the data wrangling portion of the course, and this week we're going to go with further in this course in classification models. And classification model should be the fourth part of the course, fourth part of this course. And I'm just going to provide you with a quick overview of the course in terms of providing you details on how to go about just a quick content to help you understand the different materials that we're going to cover. And then later on in the course, we will discuss the how to go about the different projects in Alteryx. This is the method I use in teaching so as to help you get the concepts first before going through the project in Alteryx. And once I'm done with this portion, I'm going to show the part that has to do with Alteryx. So classification models. What do we need classification models for? Say, for example, you have data that has been given to you, and for example, they want you to identify whether an email is a spam or not. Then you would need to use classification models to identify if the email is a spam or not. So in this case, I'm just going to go through it with you. So a quick overview: classification models are used to identify what group a data point belongs to. So like I said, we can use them for spam detection. We can use them for like I said, we can use them for spam detection. We can use them for medical diagnosis, to identify whether someone has pneumonia or not, or whether someone has malaria or not, depending on what portion of medicine you want to use it for. We can also use it to find out if a transaction that's recorded on a credit card, if it's fraudulent or not. Some of the models we're going to explore in this portion of the course would include regression model, um, that's logistic regression model, decision trees, random forest model, boosted models, and we're also going to um, evaluate the stepwise regression model. So then again, we have to go back to our business problem classification. So this would help us understand how to go about solving the problem. So say we're given a business problem and they need us to predict some outcome, and we have a data rich case where the outcome we are trying to predict is not numeric, but it's more so a categorical variable. So in this case, we're going to, so if you step down through this, you're going to see that we go through a business problem and we are supposed to predict an outcome. It's data rich and it's a categorical variable. So since it's categorical variable, we have to go with one of these two classification models. So whether it's binary, we go with logistic regression model, or decision tree. And if it's non-binary, say in this case we have to categorize data that's more than two categories, then we are looking at using a non-binary model, which is forest model and boosted model. So classification problems, like I just explained, can be divided into two different formats. The first format is binary classification. So they have two groups. It's either a yes or no, true or false, 1 or 0, success or failure, right? Then we have the non-binary classification, which has more than two groups. So in this case, we have you're trying to classify the color of a shirt. You're trying to classify what type of car just passed the road, what's the breed of the dog that you saw, those kind of things, where you have, so for example, you have a color of shirt, you have blue, yellow, red, you have different colors, type of cars, you have Ford, you have Mercedes, you have Honda, Toyota, Nissan. Those are different models of cars, and you have a lot of them. So because of it's not two variables you're trying to classify, it's called non-binary. In a case where it is two, it's called binary classification. So binary classification. So one of the models we're going to use for binary classification is logistic regression, like I explained earlier. Logistic regression is one of the basic forms of regression modeling, and it's a part of the generalized linear models, which is also called GLM. It means that the formula that's being used is very similar to that of linear regression, but it's very appropriate that we use it since we are trying to classify a dependent variable that's in a binary method. So it's we're trying to classify a dependent variable that's also categorical and it's binary in nature. So we can use logistic regression. There are two types of there are two other types of regression analysis, like logistic regression. We have the probit transformation and we have the log-log transformation. Those parts we won't focus much of those parts in this course. We'll only focus on the logic transformation of logistic regression. That's the only one we're going to focus in this course mainly. So we are very familiar with the linear equation, which is y is equal to b0 plus b1 x1, where b0 is our intercept and b1 is the coefficient of our slope, while x1 is the independent variable, while y is the dependent variable, right? We are familiar with this, but in logistic regression, we are concerned with the probability of the outcome of the outcome of the dependent variable. So usually the outcome takes the format, like we've seen, it takes the format of true or false, 1 or 0, success or failure. So we are only concerned with the probability of that outcome. And in order to get the probability of that outcome, we need to make some assumptions in order to reshape the way this equation looks like. So from probability, we know that the probability of the success of an event is P, while the probability of failure, which is Q, is 1 minus P. Based on this, we also know that the p-value range from 0 to 1, which means the p-value cannot be negative and it cannot be greater than 1. So these are basic assumptions we have in probability. Since the probability must always be positive, that means for we to convert this equation to actually be in a range from 0 to 1, we have to take the exponent of this equation, this part of the equation. From mathematics, we know that exponent function goes from 0 to 1 and it's not greater than 1. It cannot never be greater than 1. It's always within a space of 0 to 1, and it can never be less than 0, the exponential function. We can use that for this equation so as to represent our probability. So like I said, in order to do that, we say, so instead of having the equation be y is equal to b0 plus b1 x1, we say p, which is the probability, would be equal to the exponent of this equation. So p would be the exponent of this. So to make the probability less than 1, because we want it to fall within the boundary of, we want our probability to fall within the boundary of 0 and 1, but not greater than 1, what we do is we have to divide by a number that's slightly larger than our probability. So what we're doing is we're taking that value and then dividing by that value plus 1, which would give us e raised to the power of y. where y is this portion of the equation divided by e raised to the power of y plus 1. So where p is the probability of success again, and 1 minus p be the probability of failure, we have that q is equal to 1 minus p, which is 1 minus this entire equation here. So dividing p by q would have that e raised to the power of y. So if we divide this value by this value here, or this value by this value here, we'll have that e raised to the power of y is equal to p divided by q, or p divided by 1 minus p. This translates into y is equal to the natural log of p divided by 1 minus p. And basically what we are getting here is just, if we take the natural log of this portion of the equation and take the natural log of this portion of the equation, we are getting this part here. So in terms of probability, we can say that the logit of p is equal to natural log of p divided by 1 minus p. And basically all we're doing is we're just saying that this logit, which is this portion, is equal to b0 plus b1x plus b2x plus all the way to bnxn. So that's basically the y equation here, which we're doing. So here, p divided by 1 minus p is the odd ratio. It's called the odd ratio. And whenever the log of the odd ratio is found to be positive, the probability of success is always more than 50%. So what are the differences between, one may ask that, oh, we have this equation that's quite similar, but we see a slight difference. What's the difference between logistic regression and linear regression? Logistic regression is quite similar to linear regression, except for the fact that while logistic regression tends to predict whether an outcome is true or false, linear regression would try to predict the size of the variable. So in case of linear regression, we get y is equal to mx plus b, or b1 x1 is y is equal to b0 plus b1 x1. So what we are doing with linear regression is we are trying to predict the size of a variable. But with logistic regression, we are trying to, instead of predict the size of the variable, we are trying to predict the outcome or the probability of that variable. So again, instead of in linear regression, we know that we have the y and the x axis, and we are fitting a straight line through the data points so as to get a straight line. In logistic regression, we are not trying to fit a straight line. Rather, we are trying to fit an x-shaped curve that range from 0 to 1. And again, this is based on the exponential function that goes between 0 to 1. This means that the curve tells you the probability of an event occurring. So from the curve, if the probability obtained is greater than 0.5, we classify it as 1. Otherwise, we'll classify it as 0. This goes back to what we said here. Whenever the log of the odd ratio is found to be positive, the probability of success is always more than 50%. So we tend to classify the positive end of it to be 1. So when I mean the positive end of it, tend to predict anything that's greater than 0.5 to be 1. So logistic regression in Ultrix, when we go over this portion of it in Ultrix, we'll see that the p-value in Ultrix is always considered the indicator, and this is because with the p-value we can tell with the p-value, any value that is any variable that has a p-value greater than 0.05, we consider it as not statistically significant, and that means that we most likely should not include it in our model, or we have to modify the variable to include it in our model, as they don't affect they are not statistically significant to include in our model to predict the outcome. Sometimes variables also have, we've seen in cases where variables have different multiple categories or too many categories, say 5 different categories as opposed to a smaller range of category. And when we find those type of cases, we tend to remove those variables. But first, we have to make sure to look that none of those categories in that variable is statistically significant. Um, for Autrix, this is one of the places where a stepwise tool in Autrix can be used to efficiently help us reduce the number of variables to be considered in the model. For model validation, we make use of an independent data set that we call the validation set. So remember, in when we bring in our model after the data wrangling portion of it, we split our data into the estimation data set and the validation data set. The estimation data set can also be called the training data set. And we just split it 70, a ratio of 70 to 30. And validation data set is the independent data set that we always use to validate the model to see if the model is working out. So for model validation, we normally look at different metrics to consider how good our model is performing. And one of the metrics we consider is the overall accuracy. How accurate is the model predicting at the overall level? Then we are looking at the accuracy of the different class. So how good is the model predicting whether it is a yes? How good whether the model is predicting whether it is a no? How good is it predicting whether it's 1 or 0? Those type of conditions, that's what we look at. Then we look at the precision. The precision is the number of correct positive results divided by the number of all positive results returned by the classifier. We have the recall and we also have the F1 score. And those metrics are all provided in Autrix. They help us understand how well our models are performing, whether the model is performing well enough or not. And then we have the confusion metrics. So remember I talked about the accuracy of the model. So accuracy of the model is, so say we are predicting, we want to predict whether the model is predicting right. So here we are looking at, okay, this is actually negative and the model is predicting it negative. So that means it's correct. And this is positive and the model is predicting it positive. So that means the accuracy would be A plus D divided by the entire number of predictions that we have. Those are the type of information we can derive from the confusion matrix. Like I said here, I've written out all the possible metrics that we can extract from this metrics to get information that we can use to evaluate how well our model is performing. So we have the accuracy, the recall or the true positive rate, the false positive rate, the true negative rate, the false negative rate, and then we have the precision. So the precision is just basically the proportion of the predicted positive case that we are correct as calculated using this equation below. So the predicted positive rate would be D divided by B plus D. Then another one of those things that we use to evaluate our model is called the receiver operating characteristics curve. I know it's a mouthful, but they use the word ROC graph for short, or ROC curve for short. It's another way we can use to look how good our model is performing. Basically, what the curve is basically extracting the information from this portion of the confusion matrix. So what it does, it plots the false positive rate against the true positive rate. So the false positive rate will be on your x-axis and the true positive rate will be on your y-axis. And then the 0.01 is the perfect classifier. So all positives and negative cases are classified correctly in this case. The curve is basically obtained by moving the threshold using your classification. So remember here, if we went back a little bit, we said that if the probability obtained is greater than 0.5, then we classify it as 1. Otherwise, we classify it as 0. So in this case, how about not 0.5? We reduce that threshold to 0.1. Then that's going to affect our ROC curve. And if we reduce it, if we increase it slightly, so by moving that threshold, we are basically going to get different multiple data points which we can use for our ROC curve. And the ROC curve summarizes all the confusion metrics that each threshold produces. So basically, we have tons of thresholds that we can use. We can use 0.1, 0.15, 0.2, 0.25. Just think of every possible variable value that can be used. The ROC curve graph summarizes it all. And the diagonal line that is achieved on the ROC curve shows where the true positive rate and false positive rates, where the true positive rate and the false positive rate are equal. Any point on the line where any point on the line means that the proportion of the correctly classified sample is the same as the proportion of the incorrectly classified sample. And then from the ROC curve, we have something we call AUC. AUC is just basically area under the curve. And it's one of those things, one of those metrics that we can use to compare different models and understand which model is predicting very well. So usually what we go by is the model with the biggest AUC or the largest AUC or largest area under the curve tend to develop better prediction compared to the ones with a smaller AUC. And then we have the decision tree. So in the decision tree, remember I just said something about multiple models. So when we are modeling a business problem, it's always best to consider using multiple models to address the problem. And this is because you want to get some models tend to overfit the data. So you want to try it with multiple models so as to understand which model will predict better. So the decision tree is another one of those models that can be used to analyze problems. And it treats the data points as if it's a series of decisions. So it's like a flow chart. So basically, say you have a flow chart, you basically have 2 points here. So maybe you have let's just say, for example, you flip a coin. If it's heads, it goes this way. If it's tails, it goes that way. So that's basically the way the flow chart works in simple terms. So it's a flowchart structure in which each node represents a test on an attribute. Each branch represents the outcome of the test, and each leaf node represents the class label. So each branch would represent the outcome. So this way you come, this way you have yes, and then this way you go no, and then you go down the branch, you would have more possible outcome. So each non-leaf node is connected to a test that splits each set of possible answers into subsets corresponding to different test results. Each branch carries a particular test result subset to another node, and then each node is connected to a set of possible answers. So the decision tree is one of those ones where I don't want to go into the intricacies of the mathematical computations that's involved with it, because it's a little bit more complicated than the that of the logistic regression, and it's a little bit out of the scope of this course, so I wouldn't cover that. And then decision tree metrics. So after running your model in Alteryx, you would have some metrics that can be extracted from it. So the confusion metrics we've already seen, and then root node error is considered a percentage of how many of the data points went into the incorrect terminal when all the data set are validated against themselves within the entire training set. So basically what this is telling us is, although we have the model that we are creating, some data points are incorrectly classified or incorrectly predicted, and the root node error is just one of those metrics that will tell you how much of that error occurs. And then the pruning table, this lists out all the levels in the decision tree. So for example, in this part of the decision tree, you have the root node, and then you have the next level of the decision tree, right? So this is just going to list out each of the level and tell you what amount of error is in that portion of the decision tree. Okay, so for the next part of this section, we'll be going through Alteryx to discuss parts of how to go about using Alteryx to develop our models, and how to evaluate those models in Alteryx, and how what metrics we can obtain from it.